Hello, students! So, today we're going to talk about physical and chemical changes, but before we can talk about physical and chemical changes, we have to talk about what's going to physically and chemically change. So let's start with some atoms. Something to be careful about, but definitely something to know a lot about. So let's get there. So, this is a picture of atoms. It's really exciting, right? Well, maybe it's not super exciting, but you can see actual atoms here where it's very, very light, that's very dense with electrons, and electrons surround an atom. We're going to get more to that later. But those electrons, when they're really, really dense, they're going to surround a nucleus. So each one of these spaces surrounded by black, where it's very light, is an atom. This is what they look like. This is graphite, but this is what they look like. So, atoms and elements. Each element is made of one single type of atom, and they can exist in monatomic form or in diatomic form. And we've talked about that before, but monatomic, mono meaning one, atomic meaning atom, or diatomic meaning two, like oxygen gas, hydrogen gas, iodine. These are all diatomic, whereas most of the other elements exist in the monatomic form, like copper or potassium. They all exist in this monatomic form. Compounds are made of two or more different elements bonded together. Water, you know, you've had this drilled into your head. H2O, that's two hydrogens and one oxygen. And all water molecules have the exact same composition. Always going to be two hydrogens, always going to be one oxygen. That's what they look like. Our negative big guy is our oxygen, and our two positives on the side here are our hydrogens. Now we're talking about the states of matter, and you have heard this before, but we're going to add a little twist. First, we'll review. Solids, all of the particles are in a nice regular shape. They vibrate just a little bit. Anything with any energy at all is going to vibrate slightly, unless they're below absolute zero, which we have not reached yet scientifically, but we've come darn close. But all solids vibrate slightly. They have a definite shape and volume. A rock, you know how big it is, you know how much space it takes up, and they have the least amount of energy. If we move along, you're going to guess it, we're going to get to liquids. They're going to move around just a little bit more. All of those particles, all of those atoms. Ooh, look at this really fun animation. The particles still attract to each other. It definitely has a volume. You know how much space a liquid is going to take up, but it can shift around. So water in a glass, it's always going to take up the same volume, which is why we can measure it with a graduated cylinder, but it's not going to be exactly the same shape. If you tip it, it's going to move. It's going to fit the graduated cylinder or the container, and it's got more energy than solids. Let's move on. Gases. They do not have a definite shape or volume. There's something called compressible. You can make them closer together or further apart, so they don't take up a definite shape. They're weakly attracted to each other, and they move at really high speeds. Look at how fast these guys are moving. Whoa, wow, so fast. They're going to fill any container, a balloon, a zeppelin, the environment. They're going to fill the whole container, and they have even more energy than the liquids. You've heard of all of these before, but these animations were pretty neat, so I regret nothing. But let's talk about something a little bit different than what we've done before. Plasma. Plasma has no definite volume or shape. Yeah, we've heard that before, just like the gas, except all of the atoms have broken down. We're going to get into this more, but they've broken down in ions that are positive and negative. Pretty crazy, but it actually happens. These have lots and lots of energy, and the implications are pretty awesome. Because these are plasmas. Lightning, the aurora borealis, solar flares on the sun, even fluorescent lights that we use contain plasma inside them. They're high energy, they give off this energy, and it's useful and neat and pretty, and those are plasmas. So now let's talk about physical and chemical properties before we get into those changes. Physical properties deal with properties that, when observed, do not change the chemical makeup. You can go between substances and mixtures by looking at physical properties. And physical properties are like color or density. They're something that you don't have to change the element or the mixture for. You don't have to change the chemistry, any of the chemical makeup. But chemical properties, they deal with properties that, when observed, do change the chemical makeup of the substance. A big one that I always think of is burning. In order to check if something is flammable, flammable being a chemical property, you have to set that thing on fire. And it cannot be on fire. It's just on fire. You could put it out, but whatever's burned is different chemically than what you started with. It has been reacted. You have checked to see if it's flammable, but you have changed the chemistry, so it is a chemical property. So let's talk about some changes. Matter changes, obviously. Ice cream doesn't just stay ice cream. It melts. Cars rust. Water boils and turns into steam. Milk curdles into cheese. Dew forms on grass. People grow older. Cement dries and wood burns, just like they talked about before. So let's talk about some physical changes. That's where the substances doesn't change its identity. Its chemical makeup stays exactly the same. These are changes in state. If I'm going from solid to liquid, if I am melting ice, if I'm breaking something, I can break a brick, and that's going to be a physical change, but it is not going to change its chemistry. If I rip a paper, its chemistry isn't any different. But let's talk about chemical changes. Chemical changes in chemistry, notice that they start very similar. That's not a coincidence, because we're going to investigate a lot of chemical changes, a lot of reactions, a lot of properties and changes that are related to this. So a chemical change is, as you guessed it, where the chemistry changes. The chemical makeup is now different. And these are something where energy is involved. Guess what? Fire. You're changing the energy of the system. You're adding some to it in order to make that reaction go, that burn. Atoms aren't destroyed. That is the law of conservation of matter. We'll get more to it later, but they're just going to change, get rearranged, they're going to get combined, but they're not destroyed. And this is where combustion, burning, decomposing, rotting, a banana breaking down, something reacts with something, catalase, enzymes. These are chemical changes that we're talking about here. And chemical reactions, that's where you have, or reactions, that is where you have reactants coming together to make products. And there could be many, many reactants, there can be many, many products, but these are chemical reactions, and chemical reactions are chemical changes. They're synonyms. And signs of a chemical reaction, a chemical change is a color change, a gas being produced, lots of energy, like an explosion, like we saw on that very first slide. We can usually tell that lots of energy has been put out by heat or light, or if a precipitate forms, meaning you have a liquid and then all of a sudden a solid comes out of it. That is a precipitate, something that is not soluble in that liquid anymore. And I really hope that's been helpful.